So in this video, we're going to go ahead and go over significant figures. First, we're going to learn how to identify them, and then we're going to learn how to round using significant figures, and then we're finally going to go over operations with significant figures. So let's go ahead and get started with identifying them. So there are some basic rules that we can use to identify significant figures. And the first rule is any non-zero digit is significant. So automatically when you see a non-zero digit, it's automatically significant. The second rule I like to call the sandwich rule. Any zeros that are sandwiched between non-zero digits are automatically significant. So let me write some quick examples of what this means. So let's say you had 1005. So this number 1005, the two zeros that are in the middle are sandwiched between two non-zero digits. Therefore, those two zeros are counted as significant, and we would say that this number has 4 significant digits. Okay. Our third rule when you have trailing zeros, let's talk about what that means here. Trailing zeros. So if you had a number like 23,000, these zeros are called trailing zeros because they're just after all of the non-zero digits. So when you have trailing zeros and no decimal, then those zeros are not significant. Not significant. So the example I wrote here, 23,000, would only have 2 significant digits. So these trailing zeros don't count, so they're not considered significant. However, in the next rule, we're going to see how when you have a decimal, then those trailing zeros become significant. So let's talk about that. So when you have a decimal point, trailing zeros that come after the first non-zero digit are significant. So let's look at the same example. Suppose we had 23,000, but this time we had a decimal point. Just by putting the simple decimal point, we have turned these 3 zeros into significant digits. So now this number would have 5 significant digits. So that decimal point makes a huge difference. If it's there, this number has 5 significant digits. If it's not there, it only has 2 significant digits. So pay careful attention to that. And then of course for our fifth rule, any zeros that are before, any zeros that come before the first non-zero digit, and we're reading these from left to right. So first non-zero digit I'll put here left to right. Are not significant. Okay, so these are kind of the basic rules that we're going to be working with to identify significant digits. So let's go ahead and look at our first numbers here. So I'm going to go ahead and write it out like 1, 2, 3. It goes up to 14. 4, 5, 6, 7, 8. Okay. So for number 1, we have 2605.40. Just by seeing this decimal, that's the first thing we're going to look at, this decimal. This tells us that any zeros that you see after the first non-zero digit are automatically significant. So this would have 1, 2, 3, 4, 5, 6 significant figures. So 6 sig figs. Again, the 0 at the very end is called a trailing 0, and it's counted as significant because there's a decimal right there. Now let's look at number 2. That has 10,733. So you might be wondering, okay, so you have a bunch of non-zero digits, but you have the 0 right here. So is it significant or not? Well, according to the sandwich rule, whenever you have any zeros that are between non-zero digits, it's counted as significant. So this would give us how many? 6, 5, 5 sig figs. Okay. And then for number 3, we have, this is kind of a trick, so careful. 0.00420, 00420. And this one, remember, according to Rule 5, zeros that come before the first non-zero digit from left to right are not significant. And then Rule 4 tells us that when you have a decimal point, any trailing zeros that come after the first non-zero digit are significant. So in this one we have 3 sig figs. Okay, now number 4 has 990 with a decimal. So be careful, that decimal automatically turns this 0 into significant. So that one actually has 3 sig figs. You might want to fix that on the assignment. Yep, 3 sig figs. And then number 5 has 325. That's an easy one because they're all non-zero digits, so that's 3 sig figs. And then for 6 we have 0.0004, and we have a decimal point. Alright, good. Remember that zeros that come before the first non-zero digit are not significant. So in this one we really only have 1 sig fig, which is just that 4. You don't have any trailing zeros coming after the 4. For number 7 we have 3000.0. So again, be careful with this one. There is a decimal point right here. Always pay attention to decimal points. So that decimal point tells you that any 0 that you see after the first non-zero digit is automatically significant. So here we have 1, 2, 3, 4, 5 sig figs. For number 8, this is an interesting one because we have scientific notation. 9.0 times 10 to the third. So whenever you see this, you ignore the times 10 to the third and you just pay attention to this number in the front. And I know it's kind of interesting, but whenever you see scientific notation, there actually is a name for the number in front. It's called a mantissa. So it's kind of just a fun fact. So the number in front of the times 10 to the exponent is that mantissa. It's kind of an interesting fun fact. Anyway, so we're still applying the same rules here. And this is 9.0. So you have a decimal point, you got a 0 at the end, so it's 2 sig figs. And let's look at the next one, number 9. That one has 2.36 times 10 to the negative 4. Again, we're only looking at the number in front. They're all non-zero, so 3 sig figs. Okay, and the rest look pretty simple. So 1 sig fig. Be careful with number 11. That's a tricky one. Number 11 says 7.00 times 10 to the third. You have a decimal and you have trailing zeros, right? So this is 3 sig figs. So be careful with 11. 12 is good, 13 is good, and 14 needs to be fixed. Let's look at 14. So in number 14, we have 325.00. So again, you see the decimal point. That means that any trailing zeros after it are going to be significant. So any again, it's the rule says any trailing zeros after the first non-zero digit. So again, our first non-zero digit is 3. Decimal point is here. All these zeros are trailing. They're automatically significant. So you have 5 sig figs. So be careful with that one, just because of the decimal. And now we're gonna practice rounding these. So let's go ahead and look at that. So when you round sig figs, you're gonna round them the same way that you normally round numbers from elementary school. So let's go ahead and look at number 1 over here. That says 5.64, sorry, 5.7, sorry, what am I doing? 5.67498. And we want to round this number to 1 sig fig. So what that means is essentially what we want to do, we want our answer to only have 1 sig fig. So the only way to do that is to round it to the nearest whole number. Because if you rounded it to anything on the right side, you would automatically have more than 1 sig fig, and you can only have 1 sig fig. So what we're going to do is we're going to look at the whole number, this whole part, which is 5. Look at the neighbor right here, that's 6. That's 5 or greater, so it bumps this into a 6. So the answer would be 6, and that's it. No decimal point. You can't. If you were to put 6.0, that would be incorrect because that has 2 sig figs. Remember, we can only have 1 sig fig in our answer. Now let's look at number 2. That one says 0.04102. We want to round this to 3 sig figs. So in terms of the new rules for sig figs, the 0 before the decimal point is not significant. The 0 right here is not significant. So remember, any zeros that are before the first non-zero digit are automatically not significant. So we're going to start by looking at this number, 4. And we want to do 3 sig figs. So it would be 4, and then we're looking at 1, and then we're looking at 0. So this is the third one. Now we look at the neighbor on the right side, that's a 2. That bumps it down. So this would be 0.0410. Remember, it has to have 3 sig figs. So it's important to make sure you put that last trailing 0, very important. This 2 rounds down, but that doesn't mean you can ignore and just get rid of the 0, because now you would have 2 sig figs, and the problem wants you to write it with 3 sig figs. Be very careful with that. Alright, number 3. This one has 2.998. And we're going to round this to 2 sig figs. So we'll look at, so the first sig fig is this guy 2. We'll look at the next one, which is 9. So we want to look at the neighbor, see what he does to this number. It's a 9, so it's going to bump this up. Now this is already a 9, so this is going to bump 2 up, so it turns into 3. Now when you round it to 3, remember that only has one sig fig. They're trying to trick you. So what you need to do here is you need to put 0.0. Okay? The moment you put 0.0, you've turned that into 2 sig figs, which is what they're asking for. Now let's look at number 4. That one says 26,384. And we're going to go ahead and round that to 2 sig figs. So the first sig fig is right here. The second one is at 6. So we're going to start there, look at the neighbor on the right. That's a 3. That's going to round down. This number turns into 26,000. Remember, these zeros are not significant because there is no decimal point. So very important. So this is 2 sig figs. And then number 5 has, I believe that says point, right? Yeah, 37.446. We're going to round that to 3 sig figs. So we look at the first one. Okay, the second one here is significant, and the third one. Alright, so that's 4. Now look at the neighbor. That's going to round it down. That's just 37.4. 3 sig figs. Notice you can't put any trailing zeros because those will be counted as significant, and you can't have that. We only want 3 sig figs. Number 6 has 49.0385, and we want to round that to 3 sig figs. So we have the first one, the second one, and here's the third one. We look at the neighbor, it rounds down because it's 3, so this gives us 49.0. Again, the important thing is 3 sig figs, so you need to have the decimal with a 0 there. And then you had number 7. That one has 0.00794. We want to round it to 1 sig fig, so you got to be careful here. So remember, these zeros up in front are not significant. So we look at this guy, that's a 7. Look at the neighbor, that's a 9. It's going to bump the 7 to an 8. So we get 0.008. Notice it can only be 1 sig fig, so you don't put any trailing zeros after the 8. You have to stop at the 8 so that you're left with just 1 sig fig. For number 8, we have 0.006. Whoops, 0.006 008. We want to round to 3 sig figs, so we'll look at this 6 right here. So he's significant, then this 0 is significant. Okay, good. This one's significant. So this is the third one. Now we look at the neighbor, see how he's going to round it. This 8 is going to bump that 0 to a 1. So we get 0.00601. And that would be 3 sig figs. And then we have number 9. That has 825,066. We want to round it to 1 sig fig. So we literally just look at the first one and look at the neighbor. He rounds down, so we're left with 800,000. That's 1 sig fig. And then number 10 has 30.0026. You're going to round it to 4 sig figs. So to do that, we look at the sig figs from left to right. So we've got 1, we've got 2, 3, 4. So we're going to look right here. Look at the neighbor. This is a 2, it rounds down. So we're left with 30.00. Remember, it's 4 sig figs. Be careful. So the fact that there's a decimal here turns all of those zeros significant because the first non-zero digit is over here at 3. Alright, good. Now we can move on to operations with significant figures. So let's go and do that. There's some space on the back to do this. Alright, so the two main operations are multiplication and division, and the rules are the same for both of them. Then you have addition and subtraction, and the rules are the same for addition and subtraction. But the rules for multiplication and division differ from the rules from addition and subtraction. So let's go ahead and look at the rules for multiplication and division. So mult/divide. So what you do here is you write the answer with the least number of sig figs from the problem. So least number of sig figs. That's all you have to do. So for the first one we have 27.3 multiplied by 4.5. So how many sig figs does the first number have? Well, it's got 3. How many sig figs does the second one have? Well, it has 2. What that means is the product of these two numbers must have 2 sig figs. So you're going to multiply these the way you normally multiply in the calculator. So 27.3 times 4.5, that's going to give us this number, 122.85. Now what we need to do here is round this appropriately to have 2 sig figs in the answer. So be very careful with that. That's why we just did the rounding previously. So looking at this number, if we're going to round it to 2 sig figs, we start with the first one. This is significant. Second one is significant. So I can underline it. Look at the neighbor. He's going to round down. So I get 120. Notice I'm not putting a decimal. If I put a decimal, that 0 would become significant and we'd have 3. Here we can only have 2 sig figs. So that's 120. And then number 2 is going to be 4.68 multiplied by 400. So you can, first let's determine sig figs. Number on the right has 3. Number on the left has 3. Number on the right has only 1. There's no decimal here. So it's just 4. That's significant. That means that our answer can only have 1 sig fig. So let's go ahead and multiply 4.68 times 400. That gives me, and I'll go ahead and write down the whole number, 1,872. We need to round it to 1 sig fig. That means that you look at the first sig fig, underline it, look at the neighbor, he's going to bump it up, so we get 2,000. Again, that's only in 1 sig fig. I can look at number 3. That is 323 multiplied by 0.0002. Again, number on the left has 3 sig figs. Number on the right, only 1 sig fig. Why 1 sig fig? Because you've got 0.0002. So all of the zeros before that first non-zero digit are not significant. So you multiply this the way you normally multiply numbers, 323 times 0.0002. That gives us, that gives us 0.0646. I should put a 0 in front. 0.0646. We have to round it to 1 sig fig. So our first sig fig is 6. Look at the neighbor. He rounds it down. So we get 0.06. Look at number 4. That one has 4,008 divided by 2.763. Again, the rules are the same for division and multiplication. Both numbers have 4 sig figs. So we're going to round it using 4 sig figs. 63. So the number is 1,450.6. Now rounding this to 4 sig figs, we're going to go ahead and look at number sig figs from left to right. So that's the first one, second one, third one, fourth one. So this guy, look at the neighbor, he's going to bump it up, so that's 1,451. Alright, I got number 5. That is 69 divided by 7.0. When you divide, well, before you do that, let's determine sig figs. This has 2 sig figs. This one has 2 sig figs because of the decimal. That means our answer has to have 2 sig figs. When I multiplied, I got 9.85714. 2 sig figs, so we look at the first one, then look at the second one here, underline it, look at the neighbor, he's going to bump it up to 9.9. Alright, so that's basically how you do multiplication and division with significant figures. Now, we're going to look at addition and subtraction. So whenever we're working with addition and subtraction, we're going to be looking at the least decimal. So let's go ahead and do some addition and subtraction. So these are actually a lot easier because you're just looking at the least number of decimal places. Our first one has 5.72 plus 2. So normally when you add this in a regular math class, you would get 7.72. Now the issue here is that we want to round this to have the least number of decimal place values from the two numbers that we have. The first number has 2 decimal place values, right? So basically 2 spots after the decimal. This other one is a whole number. So what's going to happen is we're going to round this number to the nearest whole number. This actually turns into 8, because you might be wondering why is it done like that? Because if you're adding 2 numbers, your answer cannot be more precise than the least precise number. Since most of these numbers come from empirical observation and experiment, they're all going to be imprecise numbers. They're all going to be approximated. So when you're working with addition and subtraction with approximated numbers, your answer cannot be more precise than the least precise number used in the operation. So that is why you always go with the least number of decimals, because the more decimal place values you have, the more precise the number is. The less, well, the less precise. So this 5.72 is more precise than the 2. So the answer normally in a regular math class would be 7.72. That would be more precise than the number 2, which is not a convention that's followed. So that's why we have to round it to the least precise number. So we get 8 here. I'm sorry, rounded to the least number of decimal place values. So the next one has 500 minus 79.4. So normally when you do this, you get 500 minus 79.4. That gives us 420.6. So normally that's what we'd normally get. This time we're going to be rounding it appropriately. So this is a whole number. This one has 1 decimal value. So we're going to go ahead and round this to 421 to reflect this value here. Least number of decimal places. Now be careful, because sometimes there's an extra convention, and I'm not going to confuse you, but just in case you were to encounter this, it's possible to actually round to, when we're talking about the least number of decimal values, if you see zeros, it would be to the hundreds place. But that is something separate, and I'm not going to get into it. That would be more for like a college course. So here we're just simplifying it. We're just rounding it to least number of decimal places. So let's look at number 3. That one has 0.006 plus 0.04. That gives us 0.046. So let me go ahead and just copy that down real quick. 0.046. 0.06 plus 0.04 equals, and then that's 0.046. 0.046. Okay, so normally we get that number, but looking at our decimals, this one has 3 values, this one has 2 values. So we're going to go with 2 values, and we're going to get 0.05, because again we're rounding it. So look at the neighbor, he bumps it up to 0.05. Let's look at number 4, and that one has 83. I'm sorry, 84.3 minus 0.009. So type it in the calculator. 84.3 minus 0.009. We get 84.291. And we got to round this correctly. So again, the answer cannot be more precise than the least precise number used in this operation. This one has 3 decimal values, or places I mean. This only has 1, so our answer can only have 1. So in our answer we're going to get 84.3. Alright, and so that's pretty much how you're going to be working on the rest of these problems.